Okay, thanks for the introduction of Talia, and I'm gonna share the screen so you can see my screen now, right? Okay, so I will go through to introduce the MMDetection 3, the benchmark and the cutting edges. So I'm Wenwei Zhang from the OpenMMLab. Today, I will introduce the OpenMM 2, basically all new release in this month. And then we will go through the MMDetection 3. And finally, we'll introduce a new released repo, MMYOLO, and or newly released real-time model for object detections, aka RTMDet. So first is the OpenMMLab 2. As you can see, OpenMMLab V2 is released on the September 1st, just in this month. So you can see the architecture here. There are several foundational libraries that support all the computer vision algorithms libraries in OpenMMLab. So in OpenMMLab 1, the foundational libraries MMCV. In V2, we release MMEngine, which implements a more general and powerful training engines, and also provide the evaluation engines for all the computer vision libraries in OpenMMLab. So what's new in the OpenMMLab 2? First, OpenMMLab 2 provides a very general and powerful runner for training deep learning models. So it provides a complete support of devices, including the CPU, CUDA GPU, and Apple Silicon and APU. So in the future, we will also support more and more devices so that you could train your model in many kinds of devices. Furthermore, the runner supports many large-scale model training techniques. For example, for now, usually we use the distributed data parallel for the distributed training. And when we train the generative adversarial networks, we usually use the separated distributed data parallel. And when we train large-scale models like the Swing V2, we usually use the fully shaded data parallel. So they are all supported in the MMEngine. Also, the general runners could support many popular libraries outside the OpenMMLab. For example, we could train models in the TIMM and train models in the touch region, and we could also train models in OpenClip and detector. Flexible precision training, and we could do gradient clipping and accumulation. We could also use the training techniques like the exponential momentum average for models, and we could also try the alternative trainings in the runner. So to implement a universal runner, basically we needed to first unify the training process of the many deep learning models. So as you can see on the right, the abstract training process first need a data loader to send the data to the model. So basically, the model wrapper are like the distributed data parallel. They will put the model to the correct devices and control the training process of the model. And then there will be a parameter scheduler. As maybe you are more familiar with the learning rate scheduler. So it will, and also we implement like the momentum scheduler. So it will adjust the optimization parameters inside the optimizer. And the optimal wrapper implements the techniques like the gradient clipping and the gradient combination, and it provides a unified interfaces so that we could use a unified interface to use the optimizer to update the model parameters. So this is the basically a higher level training process. And in the evaluation process, basically we have an evaluator, and this evaluator contains many metrics like the accuracy and the mean LU or COCO AP, etc. So all these modules, they are controlled and manipulated by the runner, and to allow the users to customize the training process. We also insert many hook points in the training process. So users could implement any kinds of customized hooks to execute at these hook points to control the training process as they want. Also, the logging modules can be called anywhere inside the runner, and the message passed to the logging modules can also be passed to the visualizer so that we could visualize the training process, for example, the losses, or monitor the accuracies through the outside visualization backends like the one-weighted bias and the TensorBoard. There are several common and foundational components. So the config and the registry will control the build of the model, and the file I/O components will support the necessary file I/O on multiple backends. And we also need the distributed communication modules in large-scale model training. So basically, this abstract training process unifies the training of more than 20 vision tasks supported by OpenMMLab. And we also define the unified interfaces between the components, for example, between the data set and the model, between the model and the evaluator. So, so their interfaces are defined by the data elements. So no matter whether you are training an object detection model or for training for segmentation, they all have a very unified interface defined by the data elements. And such a training process is also general and suitable for the semi and self and weekly supervised learning and few-shot learning. Okay, so the training process is highly customizable, not only because we provide more hook points, but also because we design more fine-grained abstract modules for users to customize. So as you can see, previously in OpenMMLab 1, we basically have these modules. And in OpenMMLab 2, we add many abstract modules like the schedule, data wrapper, and model wrapper. So users could replace or customize any modules as they want to customize their training process. So this is are the three major features of the OpenMMLab 2. So based on the new training engine of OpenMMLab 2, we released MMDet 3, an important part of the OpenMMLab projects. So what is MMDetection? So basically, MMDetection is currently one of the most popular object detection libraries. It supports object detection, instance segmentation, and the panoptic segmentation. MMDetection have already become a platform, as you can see, which supports many detection-related libraries in not only OpenMMLab. So several projects in OpenMMLab, they import MMDetection as a core library, like the MMDetection 3D, which is targeted on the 3D perception, and the MMRotate, targeted on the rotated object detection, and the MMOCR, target for the text detection. And we also released MMYOLO this month, which is based on the MMDetection 3. Also, there are other libraries, they import MMDetection as a dependency, including the few-shot and the MMTracking, MMPose, and MMAction 2 for the few-shot learning, action recognition, and the multi-object tracking and pose recognition, respectively. So MMDetection 3 also has a sufficient support of deployment, and all the deployments support are implemented in the code base named MMDeploy. So deployment of the 80 algorithms are supported, and it covers the two tasks like the object detection and the instance segmentation. And then we could export the models to 5 backends like the ONX runtime, TensorRT, NCNN, PPLNN, and the OpenVINO. So basically, the support of algorithms covers many commonly used algorithms supported in MMDetection, and it covers like the one-stage detectors, anchor-free detectors, and the detection transformers, and the two-stage detectors. There are also many teams use MMDetection, and MMDetection has wide applications in both the industrial and the research. For example, it has been used for the research and development in the Tencent, NVIDIA, or Huawei, and many research teams use MMDetection for research, and it is cited by more than 1,300 papers and used by more than 100 top-tier conference papers. And it is also used by many high-impact papers like ComNext, a new generation of the ComNet, and the swing transformer, which wins the SCCV 2021 MAR prize. So there are many teams use MMDetection to win the international challenges like COCO and OpenImages and many challenges in the Kaggle. So in MMDetection 3, we have optimized the training and inference speed of many commonly used models. As you can see, the training speed of MMDetection already surpasses Detection 2 on the RetinaNet, of course, FastRCNN and MaskRCNN under a fair comparison on the 8 NVIDIA A100 GPUs. Also, we improved the inference speed of the commonly used models. So as you can see on the right, MMDetection 3 surpassed the Detection 2 on RetinaNet, of course, FastRCNN and MaskRCNN. So basically, you can use the models in MMDetection with faster inference speed, but compatible accuracies. First of all, we know that MMDetection provides many commonly used models and many pre-trained models so that users could directly use these pre-trained models for fine-tuning or for other tasks. So in MMDetection 2, the models is usually trained by the multi-scale augmentation by 36 epochs. And in MMDetection 3, we provide stronger accuracy benchmark, and we have fully improved the accuracy of commonly used models. We train the commonly used models by large-scale jittering augmentation and by 200 epochs. So as you can see, the accuracy of RetinaNet, FastRCN, and MaskRCN are significantly improved in comparison with the previous version. And MMDetection also supports many algorithms. As you can see, we support the two-stage detector and multi-stage detectors and single-stage detectors and detection transformers. So we support the FastRCN released in 2015, and till now we support the Dino, Mask2 former, and the ComNext. And we also support RTMDet, which is released by the MMDetection team, which I will introduce later, a new high precision and real-time object detector. So as you can see, MMDetection basically supports all the detection frameworks, and it provides rich backbone networks like the ResNet and RegNet, and it provides abundant general plugins like the FPN, FPG, or DCN, or empirical attention. And it also provides many sufficient training techniques like the InstaBoost and cutout. So in 2022, we also redesigned the detection transformer so that we could support more detection transformers in the future. And for backbone networks, now we support all the backbones implemented in the MM classification and the TMMM. So basically, you could use all the backbones in these two projects in MMDetection for object detection tasks. We also provide some new state-of-the-art training techniques, including augmentations like the auto-aug or the simple copy-paste. And we also support the semi-supervised training for many object detectors. And we also support the software teacher, a state-of-the-art semi-supervised object detector. So what's the general semi-supervised baseline in the MMDetection? Basically, we implement a general teacher-student framework for the semi-supervised object detection. So such a framework is firstly, we need to train on the student model on the labeled data. So we have the labeled images with the labeled arguments, and it will be sent to the student. And then the ground truth instances will take as the supervision signal to calculate the loss with the student. And the student will be updated, and it will be updated to the teacher through the EMA. And then when we use the unlabeled images, the unlabeled images will firstly be weekly augmented and sent to the teacher. And teacher will inference on these unlabeled images and predict instances. And these instances will serve as the subdo annotations and used as a supervision signal for the student. And finally, the student will be updated, and it will also update the teachers through the EMA. So such a general teacher-student framework doesn't support any structure of the object detector. So we could use it for many kinds of object detectors, and we could simply change the detector by config, and it doesn't assume any property of the dataset. So basically, we could change the dataset or use multi-source dataset for semi-supervised learning. And we implement many necessary data augmentations for the strong and weak augmentation. So here is a baseline for the or common practice in MMDetection for training a semi-supervised object detector. So we first pre-train the object detector on the COCO dataset by 12 epochs. And then we use the unlabeled images in COCO dataset and train the model by 24 epochs with a batch size of 4. So basically, the batch size contains 2 labeled and 2 unlabeled images. As you can see that we tuned the model on fast RCN, RetinaNet, Cascade RCN, and FCOS, and we can see that such a semi-supervised fine-tuning paradigm could generally improve the accuracy of the RetinaNet, fast RCN, and FCOS and Cascade RCN, and basically, which means that such a framework is generable and can be applied to these 4 kinds of detectors. So this is the semi-supervised baselines newly released in the MMDetection 3. And finally, let's go through the MMYOLO and RTMDet, which is based on the MMDetection 3. So why we released the MMYOLO? So basically, we observed that for now, we could see many YOLO series models like YOLO V5, YOLO V6, and YOLO X. However, all of these algorithms, they are implemented in different kind of libraries with different training engines. So basically, they are like the unified and convenient comparison among these algorithms. So first, we want to provide a unified platform for the YOLO series models. And we also find that in the community, there are many developers in the community, they want MMDet to support the YOLO series. So we have heard many voices in the last year. So we decided to support the YOLO on the MMDetection. However, we also find that the many YOLO series models, they use different license, like the GPL3 and MMDetection use the Apache license. So we decide to release the YOLO series models on a new report using the GPL license. So we release MMYOLO. So MMYOLO is developed by many developers from the OpenMMLab community and the MMDetection team, where the community developers takes the main part of the development. And I also want to give great thanks to the community partners, which support us to release the MMYOLO projects. And in the MMYOLO projects, we want to explore a more efficient and transparent collaboration strategy with the community. So basically, we have many attempts, new attempts that never done in the MMDetection in the MMYOLO. So we could invite main contributors outside the MMDetection team to participate in the management and the design of the whole project. And we will release a more transparent and a development plan and action items for the community so that they could choose any items they are interested for development or to participate. And the development and the design of the project will be guided by the requirements from the community. So overall, we want the MMYOLO to become an open source library targeting on the industrial applications. So first, it will be based on the OpenMMLab 2, and it will fully exploit the existing powerful runners and implemented utils in the MM engine, MMCV, and MMDetection, and other libraries. And then the MMYOLO will provide a unified benchmark for the YOLO series models like the RTMDet, YOLO V5, V6, and YOLO X, and maybe new YOLO models in the future. And in the future, we also want to explore the multitask using the based on the OpenMM libraries like the MMDetection, MMRotate, and MMPulse, and maybe MMTracking. So maybe in the future we could use like the RTMDet or YOLO V5 for the multi-object tracking or for the pulse recognition. And in MMYOLO, we also want to provide a full documentation for different levels, for developers at different levels. So we provide the getting started and provide the tutorials for the deployment, and we will describe each algorithms in detail for the beginners, and we provide many visualization tools and interesting demos for use. So based on the MMYOLO, we conduct an empirical study on existing designs and training techniques. So we release the real-time models for object detection, also called the RTMDet. And the RTM, you could also take it as the release to manufacture. So based on the existing observations and the summary of the existing YOLO series models, we found that the large kernel convolutions actually plays an essential role in the design of the basic building blocks. So as you can see, the figure A to C, they are basic building blocks in previous YOLO series models. And in RTMDet, we explore a new direction by using the large kernel convolutions. As we can see, like the many recent works, they revisit the large kernel convolutions like the RepLKNet or the ComNext. So we also try the large kernel depth-wise convolutions in the basic block. As you can see, we evaluate different kernel size for the depth-wise convolutions, and we choose 5 times 5 as a good speed accuracy trade-off. And so as you can see, the basic block, they contains more convolutions, and we want to keep a balance between the backbone and neck. And also we want to balance the computation costs at different scale features. So we reduce the number of blocks in the C3 and the C4 stages in the backbone. And we found that it achieves a better speed accuracy trade-off. As you can see, we modified the backbone to reduce the number of stages in the C3 and C4. And we also explore, there are also many kinds of design details of the model architecture, and you could refer to a code released in the MMDetection. We also try many new training techniques that is not fully exploited by previous works. So the first, we also adopt the two-stage training. For the first 280 apples, we train the model by strong augmentations, and we try the cached mosaic and the mix-up for efficiency. And we then fine-tune the model for 20 apples with the weak augmentation. And we explore a new training loss, which uses dynamic soft label assignment. And we also try better hyperparameters and training tricks like AdnW and flatten cosine learning rate. And we also pre-train the backbone by the ResNet stack spec. So overall, based on from the YOLO XS, we can see the step-by-step results from the YOLO X to RTMDet. So after adding the AdnW and the cosine learning rate, we could slightly improve the performance without modifying the parameters and the flops. And the modification of the basic building blocks in the backbone and the neck, as you can see, it significantly improved the accuracy and also add some parameters. But the inference speed, they doesn't change it much. And then we use the separate BN height, which share the parameters in the height for different scales, but use different Bayesian normalization statistics. So basically, it doesn't improve the accuracy, but it significantly reduces the parameters in the height, and without inference speed. And Finally, we add all the new training techniques like the label assign and the cache mosaic, and we use a better pre-train. As you can see, we significantly improve the accuracy of the model without without modifying the parameters or the latencies. So finally, when we compare the RTMDet with previous works, we can see that the RTMDet uses much less parameters but achieves faster inference speed in comparison with YOLO V5 and YOLO X. And there are several takeaways in today's talk of the MMDetection 3. So first, MMDetection 3 provides solid benchmarks for strong benchmark on the speed and accuracy, and it provides SOTA algorithms and training techniques in a unified platform. And we also released MMYOLO, which provide a unified benchmark for YOLO series. For the cutting edges, we also explore many new directions. So first, we upgrade our basic architecture with the OpenMMLab so that we could use a unified interfaces and the training process to provide a solid foundation for the new algorithms in the future. For example, for multitask or multimodality algorithms. And we also release a universal semi-supervised framework that can be generally applied to many object detectors so that both the academia and the industry could benefit from it. And we also released RTMDet, a new high accuracy and real-time object detector so that the users, the developers in the community could use the off-the-shelf real-time detectors from the MMDetection. So that's all for today's talk, and thank you for listening.